Our next speaker is Daniela Rus. Professor Rus is the Andrew and Erna Viterbi Professor of Electrical Engineering and Computer Science and the Director of the Computer Science and Artificial Intelligence Laboratory, or CSAIL, at MIT. Professor Rus's research interests are in robotics and artificial intelligence. The key focus of her research is to develop the science and engineering of autonomy and intelligence. Professor Rus served as a member of the President's Council of Advisors on Science and Technology, the Defense Innovation Board, and as a United States expert for global partnerships in AI. She's a senior visiting fellow at MITRE Corporation. She's the co-founder and board member of Liquid AI, Temis AI, and Venti Technologies. Professor Rus is a MacArthur Fellow, a Fellow of ACM, IEEE, AAAI, and AAAS, a member of the National Academy of Engineering, National Academy of Sciences, and of the American Academy of Arts and Sciences. She's the recipient of the Engelberger Award for Robotics, the John Scott Medal, the IEEE Edison Medal, IEEE Robotics and Automation Technical Award, and the IJCAI John McCarthy Award. She earned her PhD in computer science from Cornell University. Professor Rus aspires to help build a world where robotics and AI systems help people with physical and cognitive work, accelerate scientific discovery, and enable solutions to the grand challenges facing humanity. She's the co-author of the books The Heart and the Chip, Our Bright Future with Robots, as well as The Mind's Mirror, Risk and Reward in the Age of AI. Please welcome Professor Rus.
Thank you very much, Tom, for this very generous introduction. Hello, everyone. Today, I would like to explore with you how integrating advances in hardware with artificial intelligence enables robots to translate raw sensor data into more intelligent physical actions. So now think about robots as devices that have a body, the hardware, and the brain, the software. Physical intelligence, or let's call it physical AI, increases the brain's capabilities of robots by using AI's power to understand text, images, and other online data. And so you can think of this as being synergistic to embodied intelligence, which is about adapting the hardware or the body of the robot to the environment to achieve intelligent behavior. Now, today in the field of computing, we have two largely separate fields. We have artificial intelligence and robotics. And artificial intelligence is amazing us with its decision-making and learning, but it remains confined inside computers. On the other hand, robots have a physical presence and the ability to execute pre-programmed tasks, but they're mostly not intelligent. My objective is to bridge the separation. And with physical AI, AI will not just reside inside computers, but it will roll, it will walk, it will fly, it will interact with us in the physical world. Now, in order to make this physical AI work, we need to change how AI thinks, how machines are designed, and how they learn. It is challenging to use today's AI systems on safety-critical applications in the real world, like robots, because AI models make mistakes. And so, for example, here you can see the AI system attached to a robot car that is very good at detecting individual cars and individual pedestrians, but has trouble with groups of pedestrians. For physical AI, we need brains that do not make mistakes. For physical AI, we also need AI software that can run on small computers on the body of the machine, for example, our soft robot fish. And today's AI doesn't fit because it requires server farms. Additionally, today's AI has a very high energy cost, which cannot be covered by the batteries on board the body of the robot. So let me explain to you the energy cost of AI briefly. So today's frontier models like GPT, Llama, Claude, Gemini are very large models on the order of trillions of parameters, and they're built in two energy-intensive phases. They're called pre-training and fine-tuning. And the goal of pre-training is to have the model learn general knowledge that is embedded in the data. And the more knowledge you give the model, the better the model. large language models are typically trained on 5 to 15 terabytes of data. And the objective is to learn the weights in a huge graph, the transformer architecture, so that they can generate sentences. And so, for example, after pre-training on many facts about the world, the model could correctly predict that the next word in the sentence, the first ISCC was held in, is 1954. The second phase, post-training, fine-tuning, uses specialized data to adapt the model to be useful for specific tasks, maybe to follow instructions. And so, for example, we can fine-tune a model with all the ISSCC proceedings, and then we can ask the model to summarize papers for us. Now, to do all this training and inference, AI consumes a huge amount of energy. And on the left, you see the US data center energy consumption projected to 2030, and the data is in terawatt hours. And on the right, you see the data center share of total US power. And as we scale the AI models to get more and more capability, these numbers will continue to grow. And so the question is, what can we do to reduce the energy cost of AI? Well, one solution is to simplify the model without losing its effectiveness. And one technique is called pruning, and pruning involves removing the unnecessary nodes and edges in the model. In other words, removing the parameters that don't really matter. So another method is called quantization, and quantization reduces the precision of weights and activations in a model. And the idea here is that by representing numbers with fewer bits, quantization reduces the memory footprint and also improves the inference speed. So for instance, instead of using 32-bit floating point numbers, we can use 8-bit integers. Now, recently, DeepSeek has shown that these ideas, pruning and quantization, along with great engineering, can result in significant energy reduction of the training and pre-training of large frontier AI models. And so, in other words, they showed that it is possible to get to the best performance of a model with less energy and faster than previously thought. Specifically, DeepSeek trained a 671 billion parameter model using a series of techniques that include pruning and quantization, along with things like dropping down to PTX, the assembler language that sits just above the NVIDIA GPU. And they achieved a 45-fold increase in training efficiency compared to standard practice. This is really extraordinary. So DeepSeek showed that performant large language models can be trained with less compute and infrastructure than previously thought. And specifically, a single training run costs $5.6 million as compared to an order of magnitude bigger for today's practice. So this is great. Now we have some ideas for how to decrease the energy cost of AI. These savings can be used to continue to build larger and larger models. But here's the thing. As we continue to increase the size of these models, the thesis that pure scaling of next token prediction models will continue to increase the performance of the models is beginning to show diminishing returns from the point of view of capability. And here's some data that shows how scaling impacts the model's performance on a challenging benchmark called the MMLU. And this is raising an important question. Are there new ideas that will not make mistakes, that will result in small models, and that will lead to better capabilities than the transformer architectures? Well, in my research group, we're using inspiration from nature, in particular from a worm called C. elegans, to answer this question. In stark contrast to the billions of neurons in the human brain, the worm lives happily on only 302 neurons. And biologists know exactly the math of the neurons and the interconnections between the neurons. So here's the idea. Can we use inspiration from this math to build a new class of AI models that is physics-based and nature-inspired? So we've built liquid networks, which are compact and explainable as compared to today's solutions. Let me show you how they work. This is our self-driving car, and it is trained using a traditional AI solution, the type found in many applications today. And here's the dashboard that shows how the car makes decisions. In the lower right corner, you see the map. In the upper left corner, the camera input stream, and the big box with blinking blue and yellow lights is the decision-making engine that tells the car how to steer and how to accelerate. So you can see that the car stays on the road, but it is impossible to correlate the activity of the blinking lights with the behavior of the car. Furthermore, if you look at the lower right corner, that shows the attention map. That shows where in the input stream the decision-making engine looks in order to make decisions. And you see how noisy it is. This solution looks all over the image and is very interested, especially in the bushes and the trees on the side of the road, which is not how humans drive. Now, compare this to our worm-inspired liquid network for self-driving cars. Our solution can solve the same problem. It can drive the car with only 19 liquid neurons rather than tens of thousands of neurons. And look at the attention. It is so clean and focused on the road horizon and the sides of the road at the horizon. And because the liquid network solution is much smaller, we can also extract decision trees that give us explanations for how these solutions make decisions. So how is this performance possible? Well, in most traditional AI solutions, the artificial neuron is an on-off computation. It takes in some numbers, it adds them up, it passes them through some basic math, and it passes along the result, which is a 0 or 1. And this becomes complicated because it is happening across thousands and sometimes millions of nodes. Now, liquid networks use fewer neurons, but each one does more complex math. And this math is inspired by the math of the worm, the math we see in biology. Specifically, we use differential equations to model the synapses and the computation of the neuron. And if you plug the two blue equations into each other, we get the first equation in the big blue bubble. And this equation is actually very interesting. It is a differential equation where the term for time actually depends on x of t. And this is a very interesting property because it allows for adaptation. The other thing that's special about this equation is that it admits a closed-form approximation with an upper bound. And this means that from an implementation point of view, we do not need integrators. We can do straightforward computation while still having the benefit of the complexity of the model captured by the differential equation. And finally, this solution is actually provably causal. It means that the model learns to associate cause and effect. In other words, you have already seen an example where for the driving task, the model focuses on the task, on the road horizon, rather than the context of the task. So the other thing we do with liquid networks is we change the wiring of the neurons. And with these changes, we have some really exciting results. Now, most AI models are frozen after training. That means that when you deploy them in the physical world, they do not continue to improve. You just have to wait for the next release. With liquid networks, we get models that continue to adapt after training based on the inputs that they see. And so an interesting question here is, as you look at this model, can you figure out how to design specialized chips that can capture the computation that is needed in these kinds of AI models? And I'd like to encourage and challenge all the students in the audience to really think about how might you create specialized, customized chips for this particular type of architecture. Now, let me show you how causality and adaptation impact performance. So, for example, we have trained traditional AI and liquid networks to find things in the woods using videos like this one. Notice it's summertime. Okay, so then it turns out that all the models learned how to do the task during the summer. But then we tried the task in the fall. And the traditional AI model fails because the new background confuses the model. The liquid network solution adapts and still works in the fall, and this is because of the causality property. In fact, the solution still works in the winter, and it still works if you go from the woods to urban areas. So liquid networks are important because they get machines to think using this new physics-based technology for AI. And it turns out that the small compact models can run on edge devices like robots, like smartphones, like the computers in your companies. So here's the liquid network focused attention. Now, we have compared liquid networks to transformers on a variety of tasks. And I know you can't read the table, but I just wanted to put it there so you could see that we have extensive data about this. For the physical real-world dynamics modeling task, we get 123% improvement over transformers. And for text sentiment analysis and for information retrieval, we get 10% better performance on tasks as compared to transformers. Now, we have used these ideas to build what we call liquid foundation models at our young startup called Liquid AI. And these liquid foundational models turn out they offer the best performance in their respective classes at 1B parameters, 3B parameters, and 40B parameters. Another advantage of liquid foundational models is their reduced memory footprint as compared to transformer architectures. And here you see how the memory footprint of liquid 3B models compares. And here you can see how the memory footprint of liquid 7B parameter models compares. And so this reduced memory footprint is important because the lower memory requirements enable these models to be deployed on edge devices. Liquid foundational models are also performant, and they talk to you in a wide range of languages. Here we see Japanese, and you see a jury evaluation of the capabilities, the chat capabilities in Japanese. And here you can see a head-to-head evaluation that shows the proportion of times the liquid foundational models were preferred over other models by the jury. So this is really exciting because now we have these compact foundational models that can handle multimodal data, meaning text, video, and sensor inputs. And this brings us another benefit. We can go back to physical tasks, control tasks, or other types of physical tasks, and we can consider how language contributes to intelligence. And you see, language allows us to raise the level of abstraction and reasoning that is possible for intelligent machines. And so here's an example. Let's say we have this image, and we have some text describing it. We can build a foundational model that aligns the perceptual features and the language features of this problem, of this task, in the same latent space. And then we can train a model to control relative to some concepts. For example, we can train a model to avoid the deer using video data about the deer. And once we've trained the model, using language, we can say it with words. Now also avoid other animals and trees and cars without having to go through the expensive training with video data. And this actually gives us an energy-efficient, out-of-distribution generalization that is enabled by the abstraction we get with language. So here's how this works in practice. First, we set a textual feature, a set of features relative to, relevant to driving. Then we curate a set of textual features to be swapped in as simulation targets. And finally, we simulate the image feature by sensibly swapping with a target feature. And using this approach, we can train with expensive data in one scenario, and then we get an energy-efficient generalization to a variety of scenarios. For example, going from avoiding cars to avoiding deer, and to driving in a wide range of settings, from a different season to different lighting conditions. Okay, so now we have capable compact AI that can run on small machines and can cope with out-of-distribution scenarios. And so the other challenge with physical AI is that it makes mistakes. And so how can we ensure that there will be no mistakes, such as crashes? Well, to ensure the safety of these models, we developed a technique we call barrier net that draws a lot from the control theoretic literature. And so here's the idea. We can take a machine learning model, an AI model, any kind of model, can be liquid networks, can be anything else, and we can wrap this model with an extra layer we call the barrier net layer. This barrier net layer will force the output of the model into a safe region as defined mathematically by a human. And so we can develop models to guarantee, for example, that autonomous vehicles do not have collisions, or the output of a large language model is not toxic. The way this works is through something called a high-order control barrier function that the user defines and that is used to specify the safety of the system. And we developed a method that can transform any nonlinear optimization into convex optimizations that are differentiable and trainable in neural networks. So using these techniques, we can apply barrier net to robotic systems, for example, to robot cars that drive in challenging lighting conditions, or to robot planes that fly. In this case, safety and stability are both important. And here the task is to hit the stars and not crash into the canyon. We also apply this to multi-agent systems, where we have hundreds of agents collaborate to traverse information, a complex environment, and there are guarantees that the agents will not collide. And finally, this is a physical example where multiple robots collaborate to push a heavy object. So now we have safe AI that can run on small machines, and we can even begin to imagine and design these machines, which is another aspect of physical intelligence. So by now, I'm sure you have generated images from text-to-image systems. It turns out we can also generate text-to-robot, but not using today's AI models because they do not understand physics. Here's what I mean. So we asked ChatGPT to design a new robot that can pick delicate fruit. And here's what it came up with. Now, I have to admit, these are some very wild and cool ideas that combine robots and fruit. This one is my favorite. So let's look at it in greater detail. So first, the stem seems to defy physics. Since it's so thin, how can it even lift such a lot of weight? Moreover, by fixing the ends of the manipulator, we actually defeat the whole purpose of getting a manipulation system. And then how do we even fabricate these challenging surfaces? So in my lab, we developed an AI solution that guides the design process by checking and simulating the physical requirements. So you start with a simple language prompt, such as make me a robot that can walk, and our system generates the design, including shape, sensors, actuators, computation, the program required to control the machine, and also the fabrication files to make it. And then, using a physics simulator, the designs are refined until they satisfy the task requirements, and they're further optimized. And so, for instance, for robots that move, we might want to have a legged design, which is more optimal than the blob. And within hours, we can go from idea to controllable physical machine. We can apply this method to design a wide range of machines. For example, this one is an automatically designed robot gripper. So we can do text to robot. We can also do image to robot. This photo can be transformed into a cuddly robotic bunny. And to do that, our AI algorithm computes a 3D representation of the bunny, and then it slices it into layers. It unfolds the layers, prints them, and then we fold the printed layers. We string some motors and sensors, and we write some code, and then we get the bunny you see in this video. And so this approach can be used to make almost anything from a photo. Now, using AI to do text to robot or image to robot is important because we are drastically reducing the time and resources needed to prototype and test new products. And this is allowing for a faster innovation cycle. And now we can even make the leap to physical intelligence by having these new machines designed by AI that can run liquid networks on top of them learn. And they can learn from humans how to do tasks. You can think of this as human to robot. In our lab, we created a kitchen laboratory. And we instrumented people with sensors and collected a lot of data when people executed regular kitchen tasks. We collected pose, muscle, even gaze when people perform kitchen tasks. Now, we need this physical data because video alone does not capture the dynamics, the forces and torques involved in this kind of physical interaction. So once we have the data, we then use AI to learn from this data how to get robots to perform those tasks in a less mechanistic way and more human-like way. And the end result is machines that move with grace and agility, as well as adapt and learn. We can teach robots to do food preparation, cleaning, and even more using data from humans. So the ability to turn photos and words into functional machines, coupled with using liquid networks to create powerful brains for these machines that are small, that can run on device, and that can learn from humans, is incredibly exciting because it means we can build almost anything we imagine. Now, today's AI has a ceiling. It needs server farms. It has a high energy cost. It makes inexplicable mistakes. When AI moves in the physical world, we need solutions that can fit on the body of the device, that do not make mistakes, and that are compact and causal. And when we do this, we will see incredible breakthroughs and benefits. We will have personal assistants that optimize our routines and anticipate our needs. We will have bespoke machines that can help us at work. And we will have robots that delight us in our spare time. The promise of physical AI is to transcend our human limitations with capabilities that amplify our strength, refine our precision, extend our reach, and grant us the ability to interact with the physical world in ways we have only dreamed of. So to get there, we need to develop physical AI, and physical AI demands a paradigm shift. It requires compact, safe models. It requires causality. It requires understanding. It requires a bridge between the digital world and the physical world. And emerging ideas like liquid networks and other new ideas in the realm of state space models for AI illustrate the potential of physics-based approaches to AI. Now imagine if in addition to all these model innovations, we also had chip innovations, where we had AI chips that are carefully tailored to liquid networks and to other state space models. The potential is huge, and I would like to invite all the students in this community to join us, to help us build this new generation of AI chips that are tailored to state space models and that enable physical AI. Thank you very much.